I'm going to keep this brief, but that doesn't mean that Jim hasn't done a lot in his career so far. But he has made significant contributions to better understand climate variability, and climate change, with an emphasis on the mechanisms, predictability, and impacts of climate variability. And more recently, I think in the past 5 to 10 years, he's made significant contributions to understand the risks, benefits, and even the politics of climate intervention, which is what he'll focus on in his talk today. Prior to CSU, Jem spent 28 years, I think I calculated that correctly.
I think that's right.
Yeah, at the National Center for Atmospheric Research, or NCAR, and he conducted research there in all scientist career levels. He was also the chief scientist of one of the most widely used global climate models, CESM. He was the director of 2 laboratories within NCAR and was also the NCAR director for 5 years. He's an AGU, American Meteorological Society, and Royal Meteorological Society Fellow, and he's won multiple prestigious awards. However, I would say it seems that the award he's most excited about is having the best decorated house in his neighborhood.
Oh, no.
During the Christmas season.
Oh, no.
Did you win this year?
I did not win this year.
Oh, no.
Oh, we have competition.
And on a more personal level, I have been able to get to know Jim over the past few years, first as a postdoctoral advisor and now as a mentor. His advice has been really key for me and my career, and I hope you all get to interact with him during his visit today. Thanks for being here today with us, Jim, and I'm really looking forward to your talk.
Thank you very much, Danielle, and it's an honor to be here. I really appreciate the invitation. It's always great to see Danielle, and yes, I had the pleasure of working with her for a couple of years while she was at NCAR in the advanced study program. So, I'm really excited to share with you some of the work we've been doing at Colorado State on this topic of solar climate intervention. I want to get to that a little bit later in the talk. What I thought I'd do at the beginning is just try to kind of set the stage for what this is all about and why it's a topic of growing importance and really national and international dialogue. A lot of governments around the world are asking questions about this, where the science stands and whether or not something like this is a plausible idea to pursue. And I firmly believe to answer that question, I think we have to step up and be able to answer that question, but that requires research into the topic. So I'd just like to share some of those thoughts with you today. So thank you very much for this opportunity. I want to begin with this slide. This is a picture that was taken just a week ago. And I'm holding a birthday cake because a week ago I turned 63. And the reason I'm sharing my age will become apparent in just a little bit. But everything that I'm showing you today is due to, my ability to work with really a terrific group at CSU, a number of graduate students and postdocs. This is my research group at CSU. And they're just a fantastic group. Danielle was a part of this for a very short period of time. So really appreciate the people that I get to work with at Colorado State. So why are we considering this topic of geoengineering or climate intervention? And I'll define that terminology a bit more in a few moments, but the key reason is because we continue to increase carbon levels in the atmosphere through emissions of greenhouse gases, including carbon dioxide. This is a very famous curve. I'm sure many of you are very familiar with it. Measurements of carbon dioxide at Mauna Loa Observatory taken by NOAA in Hawaii clearly show that there's a continuing increase in carbon dioxide levels in the atmosphere. Carbon dioxide has increased more than 50% since pre-industrial times. So going back to my birthday 63 years ago was 1962. And carbon dioxide concentrations in the atmosphere were 318 parts per million by volume. And today, they're somewhere around 424, 425 parts per million by volume. So there's been this sort of relentless increase in carbon dioxide levels. And the impact of that is multifaceted. There's many different impacts from increasing carbon dioxide levels in the atmosphere. One of those impacts, one of the results of more energy being trapped in the Earth system, is that the climate system warms. This is another well-known curve, maybe not exactly this plot, but versions of this plot I'm sure you're all very familiar with. And it shows that there's a lot of climate variability. There's a lot of up and downs from one year to the next, or maybe even from one decade to the next. But all of that variability is now superimposed on a very clear warming signal. This is globally averaged temperature data that is expressed as a departure or an anomaly from the long-term average between 1850 and 1900. And you can see that 2023 and 2024 are the warmest years on record. The 10 warmest years on record have all occurred in the last decade. And so we have a very clear warming signal. And what this means is that we have extra energy in the system. The Earth has a fever, if you will. And what that does is stress both human and natural systems. And as the Intergovernmental Panel on Climate Change, IPCC, as well as US National Climate Assessments have clearly demonstrated in recent years, this is taken from the most recent IPCC report, is that we're seeing the impacts of this warming now in every region across the globe. The impacts that we are seeing cannot be explained in any other way other than this anthropogenic influence on climate. This includes things like extreme heat events. A warmer atmosphere also holds more moisture, so we see extreme rainfall events, drought, but Danielle is an expert in fire weather events, more frequent, longer lasting fire seasons, as well as impacts on the ocean. A warming of the ocean with depth, all the way through the depth of the ocean, plus acidification of the ocean as well. And what this means is that every additional bit of warming really matters. For every 10th of a degree of warming, the impacts become more severe. This is a plot. These kind of plots have also been part of the IPCC assessment report for some time. This is a plot from a 2018 special report that shows impacts across a range of natural systems as well as managed systems, and even things like projected impacts on tourism and human health and crop yields. The key point of this diagram is that as this warming continues, these kind of impacts are projected to become worse and worse. We're right here right now. That should be a 1.2. Sorry about that. 1.2 degrees of warming. This is sort of where we are on this so-called ember diagram. And of course, the nations of the world came together back in 2016 and worked on something called the Paris Climate Agreement, where nations tried to commit to reducing emissions of greenhouse gases to try to prevent the warming from reaching the upper levels of this current diagram, the warming between about 1.5 and 2 degrees C. Ideally, could we reduce emissions quickly enough and at a big enough scale to maybe avoid something like 1.5 degrees of warming? That now appears to be exceedingly unlikely. The Paris Climate Agreement talks very much about, you know, at the worst case, let's do everything we can to try to prevent that warming from exceeding something like 2 degrees. So we need to cool down the planet. So how can we do that? What are the possible approaches that we can take, right? I see snickering, everyone like to make Earth cool again, right? So yes and no, yes and no. Okay, so really, due to our understanding of the physics of the climate system, there's really only two possibilities. The first is what we talk about a lot and what the Paris Climate Agreement is all about. And we have to reduce emissions of greenhouse gases. We have to reduce concentrations of atmospheric CO2 and other greenhouse gases. That would allow more long-wave radiation to escape from the planet. That would cool the planet down. We've known about the greenhouse gas effect for many, many years, going back to the 19th century. We're adding more greenhouse gases. This again is the root cause of the additional warming that we've seen in the climate system. So ultimately, the solution to climate change is this: reducing concentrations of CO2. So we can do that by reducing emissions. We can also do that through carbon dioxide removal, which is one form of climate intervention or geoengineering. And I'll touch on that a bit more in just a second. One problem with this is that these approaches, even if we take an optimistic view and say that we take aggressive mitigation actions and begin to reduce greenhouse gas emissions and eventually lower those concentrations, maybe through large-scale deployment of carbon dioxide removal techniques, this is going to take decades into the future until we begin to see the climate benefits of doing that, which has increased attention then on the second possibility. The second thing, and this is not a new idea, it's been discussed for at least 50 years in the climate literature, is maybe as an additional plan, we could think of ways to reflect additional sunlight away from the planet, make the planet brighter, increase the planetary albedo. And the interesting thing about this idea is that we believe that we could do this relatively rapidly. It would have a very rapid impact on global temperatures. That's a very broad statement to make. There's a ton of nuances behind that statement, and I'll try to highlight some of those as we go through this talk today. I want to emphasize that the world, the global society, has made progress in mitigation. I'm not saying that we're not making progress in this area. We certainly are. If you look at some of the climate change trajectories of 10 or 15 years ago, we're no longer on some of those sort of nightmarish, worst case, business as usual scenarios. We are making progress. But the reality is that even if all of the nations, including the US, who signed the Paris Climate Agreement back in 2016, were to meet their targets, to meet their commitments, we would still well exceed that 2 degrees level of warming. That's just the reality of where we stand. In fact, if all the nations do what they committed to doing back in 2016, we're probably looking at somewhere closer to 3 degrees of warming by the year 2100. To put that in perspective, that's almost 3 times the amount of warming we've experienced today. So all of the studies, all of the research that goes on here and throughout the community, looking at the impacts, the growing impacts of climate change, we're thinking about a world that's roughly 3 times, has seen 3 times the warming relative to pre-industrial times than we've seen today. So that's the reality of where we are. Hopefully we can, as a global society, continue this push and even increase our ambitions toward greenhouse gas emission reductions. But given the growing risk of climate change, seeing the impacts of that throughout global society, we're to a point in time where this topic of climate intervention has really received renewed attention, renewed focus. And so it's very important for us to better understand through solid research what the feasibility, what the efficacy, what the risks of doing this, as well as the potential benefits might be relative to the risks that we know that climate change presents to us. Okay, so how do we define geoengineering? And here I use the word climate intervention, and I'll explain that in a little more detail. This cover here, if you haven't seen this report and you're interested in this topic, this is a really kind of landmark report that was produced by the Royal Society in the UK back in 2009, where they talked our state of understanding of both solar or sunlight reflection techniques as well as carbon dioxide removal techniques. And it's a very nice report back in 2009. Even though it's a little more than 15 years old now, I think it's still very, very relevant. And in that report, they present a definition of geoengineering. The title of the report is Geoengineering the Climate. So using the phrase geoengineering, they define it this way. And these words are very important. It's the deliberate, okay, so this is something we would do intentionally. One might argue that through the burning of fossil fuels and changes in land use characteristics, the impacts we're seeing on climate in some sense are unintentional, right? It's the result of us doing that. This would be deliberately intervening or interfering in some way with the natural system at a large scale, because climate change is a global problem, to try to counteract the anthropogenic climate change signals and impacts. So that's the idea behind it. Why do I prefer the term climate intervention? Well, the reason that I prefer the term climate intervention is really well articulated in a pair of National Academy of Science, National Research Council reports that came out a decade ago in 2015. And what these studies that focus both on carbon dioxide removal approaches in this report and sunlight reflection or solar climate intervention approaches in this report argued was that the term geoengineering sort of presents maybe a level of control that is illusory. And they felt that climate intervention was better terminology, because intervention means we're going to try to do something that we hope improves the situation in some way, but we're not entirely certain what the outcomes of that would be, okay? That there's question marks about our detailed knowledge. And I believe that that's probably a more accurate representation of where this entire field stands now. Even when we think about things like carbon dioxide removal, which in many ways addresses the fundamental cause of climate change by reducing concentrations of greenhouse gases in the atmosphere. When we talk about scaling those approaches up, there are major question marks about the social acceptability of that, what the environmental impacts of large-scale CDR removal might be. And so I tend to prefer this terminology. So these are the 2015 Academy reports. I'm not going to talk about carbon dioxide removal in this lecture today, but there's been two subsequent reports. If you would like to at least read the executive summary of these National Academy reports, in 2019 was a very good report that was put together on negative emission technologies and reliable sequestration. It largely focused on land-based approaches, where there's two approaches. Well, let me go ahead and show. And then in 2021 was a report that went into more detail on ocean-based CDR. CDR approaches generally fall into two categories: enhancing natural sinks of CO2. You can think about things like reforestation as an example of that, or technological approaches like direct air carbon capture and sequestration. And these reports go into quite a bit of detail on that. Also in 2021 was a more careful and thoughtful look at reflecting sunlight. And this report from the academies came out in 2021. I had the pleasure of serving on this committee. This was the charge. I'm not going to read the words. You can read while I speak to this report very briefly. This was a really interesting National Academy report that I had the opportunity to serve on. Often when the academies calls together a panel of people working in an area, so-called experts on a particular topic, there's sort of agreement in the room on we are all working in this area and this is something we need to refine. What are the big outstanding challenges in this particular area and the like. This report had a very different feel to me. There were 16 members of the committee. There were a few people like myself that had a background in sort of physical, in the physical climate sciences, but there were also legal scholars. What are the legal implications of this? There were governance scholars. If we do solar geoengineering, solar climate intervention, what are the governance considerations? How do we think about governance in the context of this? There were political scientists thinking about social acceptance. Are people accepting of even doing research in this area? So it was a very diverse panel. And even after 2 or 3 Academy panel meetings, I had no idea what this committee was going to recommend in terms of whether or not this was an area that we wanted to recommend to the US government, because the Academy can only make recommendations to the US government. Was this something the US government should invest in or not? And I'll come back to that a little bit later. So if you put all of this together in kind of a schematic, this is the way in which this topic is most frequently thought of right now. And the idea is that, you know, the good news is we're no longer really on this just ever increasing high emission trajectory as a global society. We are making progress in mitigation. We are, if you will, beginning to bend this curve. And ultimately, we need to be reducing emissions. We need to combine that probably with large-scale CO2 removal so that eventually we reach a point where the amount of carbon in the atmosphere is going to allow us to maintain temperatures at some, quote, acceptable level. Now, what this level is, what this temperature target should be, is a great question, right, in terms of governance, right? Who gets to set the global thermostat? But let's say that we do want to keep it at something like 1.5 or maybe 2 degrees of warming. Then the idea is that eventually we're going to get there, right? Hopefully we're going to get there eventually, but it's going to take some time, probably many, many decades from now. So should we consider the possibility of doing something like stratospheric aerosol injection or some form of solar geoengineering to avoid the impacts that come with this temperature overshoot above this temperature target until CO2 levels are at safer levels in the atmosphere? That's the basic concept behind it. So if we think we could do something like this that would avoid or help mitigate many of the worst impacts of climate change, is this something that we should consider doing? And that's the essence of what a lot of this research has been about. This research is not entirely new. I just wanted to put up a little bit of the history. It was first really discussed in the climate literature back in the 1970s, 1974. Mikhail Budiko, who was a Soviet climatologist at the time, was talking about anthropogenic climate change more than 50 years ago and saying, you know, this is going to be a growing problem as we move into the future. I'm not convinced, Mikhail was not convinced that as a global society, we would be able to do the things we need to do to reduce CO2 emissions. And so maybe something like solar climate intervention or solar geoengineering should be considered. Wally Broker, a very famous oceanographer, had a long, very distinguished career in oceanography, the Atlantic meridional overturning circulation and things along those lines. Also discussed this idea in the 1980s. Tom Wigley, when he was at NCAR, wrote some papers on this topic. Others have as well. But really, maybe the paper or the essay that made people really think about this was written by Paul Crutzen back in 2006. Paul Crutzen is a Nobel Peace Prize winning, or was, he passed away a few years ago, atmospheric chemist. And he wrote what's called the escape route essay that really expressed sort of his concerns that our attempts to limit greenhouse gas emissions was going to be really, really difficult to achieve. And so we needed to at least discuss and think about and research a contingency plan. And that would be solar geoengineering. And even more recently, do you guys know who this is? Jim Hansen, right? So Jim Hansen, who of course is very famous, not only as a researcher, but testifying in front of Congress back in 1988 about what the future held in terms of anthropogenic climate change and his concerns over that, has been a long-time advocate for fixing the problem through emission reductions. But he had an article in Science Magazine back in 2022, and this was a quote, I won't read it, but he was basically also saying, I think we've reached a point in time where we're going to have to do something else. We're going to have to implement some sort of contingency plan around this idea. So this is a figure from the Academy report that I referred to that outlines major solar climate intervention approaches. There are other approaches, and the report discusses those, such as increasing the albedo of the surface, painting rooftops white, painting roads white, planting crops that have a higher albedo that would reflect more radiation. There are also ideas about putting mirrors or reflective particles into outer space to reflect sunlight before it even reaches the Earth's atmosphere. But most of the research is really falls into the categories of thinking about stratospheric aerosol injection and marine cloud brightening And there's been some research around this topic of cirrus cloud thinning as well. That's not really solar climate intervention in the way that I've defined it, or the way the Academy defines it here, because thinning cirrus clouds, if we could do that, would allow more long wave radiation to escape to space. Whereas these other two approaches, marine cloud brightening and stratospheric aerosol injection, are about reflecting sunlight back out before it really enters into the Earth system. And both of these ideas are based on the importance of aerosols in the climate system, right? And we know, even though there's uncertainty and there's challenges in completely representing aerosol processes and climate models, we know that aerosols, the net effect of aerosols, not all aerosols, but the net effect of aerosols in the climate system is to cool the planet, primarily through two approaches. One is directly scattering sunlight in all directions. So some of that sunlight escapes back out to space. And then the so-called indirect effect of aerosols, where they can essentially brighten clouds and increase the albedo of clouds. We estimate right now that aerosols have offset about a third of the warming that would otherwise have occurred if it was only a response to greenhouse gases in the climate system. So I'm not going to talk about this. I don't actually do research on marine cloud brightening, but it is a major topic that the community is really focused on. And the idea is to increase the reflectivity of clouds. And where will we target those clouds? Well, the main area that's been thought of are the stratocumulus cloud decks, the semi-permanent cloud decks off the west coast of the continents. You know about the clouds off of San Diego and San Francisco off the California coast. And the analog of ship tracks is what you see as these cloud streaks here. This is due to emissions from ships of opportunity as they're moving cargo and the like. This is a picture of the North Pacific Ocean. So the idea is, could we add aerosols to these clouds that would form more water droplets and therefore brighten the clouds? But this is a challenging topic. There's a lot of work going on in this area. It's very interesting research. I'm not downplaying the importance of that or the potential of this as a solar climate intervention approach. But it's a challenging topic to study because there's a lot of uncertainties around aerosols. Cloud aerosol interactions are not well represented in climate models. There's a wide range of results from climate models. And so it makes it, climate models are the main tool that we have to do these things, right? There's not a lot of social acceptance for us to go out and say, hey, we're going to do this big perturbation experiment and we hope everything's okay, right? So we want to study these things to the best of our ability using lab experiments and using climate models. But this is a very challenging topic to look at. The other idea that's received probably more attention and perhaps the best studied and best understood approach, although there's still major questions and uncertainties, is stratospheric aerosol injection, where the analog to something like stratospheric aerosol injection is a volcanic eruption. If you have certain types of explosive volcanic eruptions, they produce an aerosol layer in the upper atmosphere above the troposphere, where the weather occurs above that into the lower stratosphere. And we see, using volcanoes as a natural analog, we see that volcanic eruptions can have a cooling impact on climate. And this is probably the most discussed example because we had relatively good observations of Mount Pinatubo, which erupted. I always think 1991 isn't that long ago. And then I look at how young so many people are in the audience and realize half of them weren't even born in 1991. But anyway, this is the eruption of Mount Pinatubo in the Philippines in June of 1991. And this is a tracer of lower atmospheric temperature change. And you can see a very significant global cooling of almost half a degree. And this cooling signal lasted for about 18 months or so. So the idea is, could we basically mimic this effect and inject aerosols into the lower stratosphere to maintain some level of cooling in the longer run? The other reason that this idea is discussed a lot is because we wouldn't have to be injecting things all over the planet, maybe just a few point locations. This is the aerosol plume from the Pinatubo eruption. And the point is, if you look at the calendar here, we're just about 6 months out now from the eruption, and you can see really pretty good global coverage of this aerosol. So maybe if we injected aerosols at relatively low latitudes and at even just a single point or two in the northern hemisphere as well as the southern hemisphere, we could achieve very good global coverage and not disrupt things like equator to pole temperature gradients as well. So we can do these things in climate models. This is one simulation with the Community Earth System model that was performed a few years ago in a paper that was published by Simona Tilms at NCAR in the Bulletin of the American Meteorological Society. And on the left here, you see a simulation, a climate change simulation. This is sort of that high emissions trajectory because the objective was to enhance the signal to noise ratio to understand what the impact of stratospheric aerosol injection might be. You can see the warming planet on the left and the lack of warming on the right, although you still have regional variability because of the natural variability in the system. And you can see a lot of the warming that otherwise would occur would be averted. So in principle, it looks like we could do something like this. And so these are the kind of experiments that have been done. And what my group at CSU has been analyzing indeed are these kind of global model experiments. I don't want to spend too much time on this slide, but just to give you a little bit of a background, there's been two large ensemble experiments done with CESM in recent years. The first is what I was just referring to. It's called the Geoengineering Large Ensemble, or GLENS. And here the idea was against a very high emission scenario, RCP 8.5, that produces a very significant amount of global warming, to start injections back in 2020. Of course, that didn't happen, but these runs were put together in 2016, 2017. And to try to maintain global temperatures around the levels that they were observed in the year 2020. And the more recent set of experiments is done against a background climate change scenario, SSP 245, which involves some level of mitigation, emissions reductions. It's deemed to be a more policy relevant scenario at this point in time. And then to start the injections in the future at the year 2035 to try to maintain global temperatures around 1.5 degrees C. It's around this period that CSM projects about 1.5 degrees of warming. Okay, I want to emphasize, I'm going to wrap up now by showing some of the results that's come out of my group at CSU, working with all these great postdocs and graduate students. I want to emphasize, however, results are very scenario dependent. Exactly how we do the stratospheric aerosol injection really depends on the details of the experiment really matter in terms of the results. So the worst thing that I can do here or leave you with the impression is that SAI would do this. It very much depends on what the temperature target we want to reach is, what kind of materials that we would put into the stratosphere, how often we would do these injections, how long they would continue, and these kind of factors. And the results are also model dependent. We do these experiments with climate models. Climate models are a very, very useful tool, but they're not a perfect tool. Okay, there's uncertainties in all of that, including the representation of some of the key climate processes. I talked about marine cloud brightening. There's also uncertainties with stratospheric aerosol injection, how the aerosols are dealt with in the stratosphere, how well the microphysics of the aerosols are represented, how different climate models represent connections between the stratosphere and the troposphere, where a lot of the climate impacts are felt. There are some major uncertainties in all of this as well. So in the last, 15 minutes or so? Is that about right? Yep, in the last 15 minutes or so, let me just sort of run through some of the work that we've been doing at CSU. And I would summarize our efforts at CSU thinking about how quickly could we detect the impacts of SAI on the climate system. Can we work toward quantifying some of the changes from something like stratospheric aerosol injection? And can we think about unilateral deployment scenarios? Because there's a lot of concern right now. What if there's not an internationally coordinated effort to do something like this, but there's individual states or individual actors that decide to do something like this? What would the impacts of that be? So let me first start with detection and attribution. And this is a nice way to kind of illustrate what the challenges are. In our 2021 National Academies report, we talked about detecting the impacts of this on the actual climate system. Could take many, many decades before we could do that. And we thought that was an interesting thing to look into. So if I go back to this Geoengineering Large Ensemble, which is a 20-member ensemble of climate model simulations, trying to keep temperatures around 2020 levels. And we just look at the first decade between 2020 and 2030. And we average across all 20 members, which we often do in climate science to see what the signal of the stratospheric aerosol injection is. And this is just a plot over the US. We have all these global plots. But SAI kind of does what the movie loop showed, what we would expect it to do. There's no significant temperature change when you look at the ensemble average. But of course, what an ensemble average is doing is averaging out with a large enough ensemble this very strong signal of natural climate variability, where natural climate variability can produce cooling signals or warming signals over large regions of pretty considerable amplitude. So given this, right, and nature is not an ensemble average, nature is going to be one of these 20 realizations. These are all plausible climate outcomes over the coming decade or so, right? So we're living in one of these worlds, and can we really detect the influence of stratospheric aerosol injection given this very high amount of natural or internal climate variability? So we did that using machine learning approaches, and we basically asked the question, if we train a climate model, looking at climate change simulations over the next 10 years, and we just gave the climate model a map, or a machine learning model. If we gave the computer a map of the world, could it tell us whether or not it was sampling a world with climate change or a world with climate change and stratospheric aerosol injection? So just a yes, no answer, and could it get it right? And again, to kind of demonstrate the challenge of this, if you look at the ensemble mean and you just look at the year 2030, just 10 years after deployment, and you look at something like extreme temperatures, okay, not just average temperature, but the 95th percentile of temperatures around the globe, you see the blue colors here everywhere, which shows that SAI is reducing the magnitude of extreme temperatures everywhere across the globe. But if you look at individual ensemble members, this is ensemble member number 1 under the climate change scenario in 2030. And this is ensemble number 1 with stratospheric aerosol injection. And this figure in the lower left shows the difference between the two. And you might say it would be really hard for the computer to say, is this an SAI world or not, right? But it turns out that if you actually do this exercise, what we find, and I'm not going to explain all these colors over here, but the solid colors mean that the computer is getting it right. And we find that within just a few years, the computer can reliably and very accurately say, this is a world with SAI. And the reason is because the computer is learning spatial patterns that are characteristic of an SAI world, and how those spatial patterns of temperature are different from a climate change world. We've done this regionally as well, but it's very interesting that we can really see the impact of SAI in only a few years after deployment on things like extreme rainfall. Now, we can also use these techniques to look more generally at how different an SAI world would be if we're kind of doing this, if we're doing stratospheric aerosol injection in some way to kind of preserve the climate state. We talk a lot about maintaining global mean temperature at, say, 2035 levels, but how would other characteristics of the climate system be maintained? This is a complicated diagram, so I'm just going to try to walk you through it very generally. You see a whole range of variables down here, and then you see this y-axis that's labeled accuracy. And accuracy is basically how well can the climate model distinguish, or can a neural network distinguish between a world with SAI or a world without. So where the machine learning model is not very accurate, you know, it's kind of flipping a coin. I have no idea. I'll say it's an SAI world, but maybe it's wrong. Means that it's really preserving pre-deployment current climate characteristics. And this applies very much to things like extreme rainfall. Everywhere else, what the pink dots signify is how accurate the neural network is in saying it's sampling a climate change world, and the blue dots a world with SAI. And where SAI is lower on this curve, it means that an SAI world is more like the current climate, but it's not identical. The computer can still say, it's, you know, in terms of this variable, for instance, 85% of the time, it's right in saying it's not the current climate. It's an SAI world, but it's not the current climate. And the way that you think about that, so let's go back to something like annual mean surface temperature. I've already shown you, hopefully, that we can preserve the annual mean temperature. But the neural network says, yeah, but it's not today's climate. And that's because these regional patterns, there's still circulation changes and whatnot. And those are very important to understand. For other variables like ocean acidification, stratospheric aerosol injection has no impact on that at all. It's not affecting the carbon levels in the atmosphere. And so there's there's big differences even in an SAI world from the current climate. We've also kind of embraced this idea of natural variability, and we wrote this paper that appeared in the proceedings of the National Academies. This is Pat Keyes at CSU. This is Noah Diffenbaugh, who is Danielle's former PhD advisor at Stanford, Libby Barnes, a colleague of mine, and Curtis Bell at the Naval War Academy. And we just took a very simple approach, and we looked at an ensemble of simulations. And these are the simulations where SI deployment starts in the year 2035. And we looked at grid points around the globe, but this is just one example from a grid point near Beijing climate, China. And we said, you know, the role of natural variability is very important. We could be in a world where a particular region or location was experiencing a bit of a cooling trend. Excuse me. And then when we start SAI deployment, you see that it begins to warm. So we call this rebound warming. Or maybe we're in a situation where the climate seems to be warming a little bit at this location and it continues to warm. Both of these, I would argue, would be potentially viewed by society as perceived failure. If we're doing this to cool the system down, how come it's not cooling down where I live? How come it's not cooling down in Austin, for instance? And you can come up with you know, other scenarios as well. And then we just simply quantify that in terms of the probability, if you will, of perceived failure. And the red regions show where roughly half of the time, even after the injection of stratospheric aerosols, you may experience local or regional warming. And I think this has very important sort of socio-political kind of consequences. If the world were to decide to do this, we have to be aware that it doesn't mean that warming signals are going to stop everywhere because of the role of natural climate variability in the system. Okay, moving quickly to quantifying changes in Earth system, in the Earth system. I'll let Danielle explain this. So I had the opportunity, the great pleasure of working with her for too short of a period of time, but maybe we can stay collaborators on things as we move into the future. But of course, she's a world expert thinking about fire weather event frequency and how climate change can impact fire weather events moving into the future. So this is just one figure from a really nice paper that Danielle led. And what we looked at, again, are these simulations looking at stratospheric aerosol injection beginning in 2035, relative to what we see in a climate change scenario. And here she's looking at a 20-year period, mid-century, 2050 through 2069, and looking at changes in fire weather event frequency. And you see over many parts of the world, you see these blue colors, including over the Mediterranean region, where there's decreases in fire weather because of lowering temperatures and maybe a bit more rainfall in some of these regions. But it's not a uniform signal. There's other parts of the globe where there's not very much of a change at all, say over portions of the Western Amazon or over West Central America or over parts of Northern Australia. And this finding that, you know, it's not going to reduce fire weather event frequency, again, speaks to local kind of circulation changes and the uncertainty from that. And if you just look at something like rainfall from these simulations, you can see that, for instance, there's still a drying signal over Western Africa and over the Amazon in a world with stratospheric aerosol injection. So, you know, these are very important aspects to try to understand. Okay, I'm going to have to really speed up here the last couple of minutes. We've also looked at things like Arctic permafrost extent and volume, and the simulations with stratospheric aerosol injection are given by the blue curves. The climate change scenarios are given by the red curves. The take home, this is Ariel Morrison, who was a postdoc at the time. She's now a research scientist working with us at CSU. And the key point is that even with stratospheric aerosol injection, permafrost extent and volume continue to decrease after deployment, especially at the southern boundaries of the permafrost, where there's already been a lot of warming and a lot of permafrost degradation, and SAI would not be enough to reverse that. She's then taken this work and also looked at Arctic shipping. I won't go through this slide in detail, but it's just talking and thinking about navigability of the Arctic Ocean as we go into the future. And so if you look at the climate change scenario in the upper diagram here, we're looking at changes in sea ice thickness going into the future. So you see big decreases in sea ice thickness over the Arctic. These are the number of days that you would be able to navigate if you were operating a shipping company across the Arctic Ocean. So a big increase in navigability moving into the future. If you look at the ARISE 1.5 scenarios, essentially, maybe you see what you would generally expect, that there's not these big changes in sea ice thickness. So sea ice coverage, sea ice thickness is pretty well preserved. Some changes, some regional changes in navigability. But if you look at a cooling scenario where we actually say, let's don't keep the climate at 1.5, let's cool it down to, say, a degree of warming relative to pre-industrial times. Now you see there's increased sea ice thickness with decreases in navigability. So I think it's important to kind of think through all these different scenarios when we think about if this is something we want to do, at what level would we want to do it? This is also a really nice illustration of this, and I'm going to give a very high-level description of this. This is a PhD student in my group, Danielle, who has also been looking at global ecological risk. And he's measured that by this parameter called climate speeds. Essentially, how quickly would ecosystems need to move to be able to maintain the climate state in which they've evolved. And in the ecological literature, it's widely viewed that, you know, no species on Earth can deal with climate speeds sort of greater than 10 kilometers per year. If you look at the role of natural variability by looking at simulations of the last 1,000 years, you see that no 20-year period ever exceeds a rate of temperature change where more than 10% of the global oceans and the global land surface is exposed to climate speeds at this level. If you do something like the 1.5 degree scenario that we're examining, it maintains climate speeds at this very safe level, but either through global warming scenarios, here also looking at the United Kingdom's Earth system model, or through stratospheric aerosol experiments where cooling is imposed, like cooling the planet down to 1.0, presents very risky climate speeds. So it would be very damaging to global ecological systems. And that can be summarized this way. So it's not only that there's a risk from climate warming to ecological systems, but if we were to implement SAI in such a way that we would rapidly cool down Earth's temperature, this would also present very damaging climate speeds. Super quickly, we've been working to look at how stratospheric aerosol injection might impact things like the weather, okay? And in April of 2011, there was a super tornado outbreak. We can actually simulate this with a weather model. These are observations of rainfall in the top row and simulated with a weather forecasting model in the bottom diagram. So what we can now do is take this weather forecasting model and we can say, what if these storms happened in the future under a climate change scenario or under a scenario with stratospheric aerosol injection? And we can begin to look at the actual impacts on mesoscale weather systems, which I think is a really, really important topic and a really novel topic. I'm not aware of any other group that's been looking at this. And so you can look at various atmospheric variables like precipitable water, all the water in a vertical column, or rainfall rates, or maximum updraft velocities in these thunderstorms. And what we're finding is that under stratospheric aerosol injection scenarios, it sort of maintains the current climate or the current magnitude of weather systems in the future as well. Whereas under climate change scenario, these weather systems become more intense. And it's not quite as straightforward as that because there can be changes to the mesoscale dynamics themselves, but this is the outcome. The very last thing that I want to say is that with only one slide, We're also looking at the importance of sort of unilateral deployment scenarios. Everything I've talked about is very idealized. The world comes together. We agree that we want to maintain temperature at some level, but the real world doesn't really work that way. And so there's a lot of concern that maybe some region is experiencing climate change impacts, like Australia is doing forms of solar climate intervention right now in kind of a desperate attempt to save the Great Barrier Reef. So what if someone did something that's going to affect the global climate system? What might that look like? So we've been exploring that. This is a paper that is in review right now. The first round of review comments were pretty positive, so we hope it's going to be accepted. We're using something called game theory to explore geopolitical scenarios. Who might be likely to do this? What would their motivation be? Would they be willing to stand up to perhaps international sanctions for trying something like this? And then we can take those kind of scenarios, run it through a climate model simulation, develop a storyline that how might the climate evolve, and depending on how the climate evolves, would there be a response to this? Some sort of a response, maybe some other country would implement this. And so this is really, really interesting work that I just don't have time to go through today. So there's a lot of unanswered questions, including ethical questions and governance questions on this topic. But what I want to conclude with is that there research on this topic, I think, is here, and it's going to be here for a while. So even though there's a lot of uncertainty, I think that the global community is moving in the direction that the U.S. academies in this 2021 report recommended, that the U.S. develop a research program in this topic because it is a topic that's being widely considered. The American Meteorological Society essentially said the same thing in a policy statement a few years ago, that there needs to be an accelerated and robust climate intervention research program to inform policies, to be policy relevant, but not policy prescriptive at this point. The United Nations Environmental Program wrote a report a couple of years ago that said the same thing from an international standpoint. I've been very involved with the World Climate Research Program throughout my career, and just about a year ago, they started a new major initiative from a global international perspective to try to understand the risks and the benefits of proposed climate intervention approaches relative to the risks posed by climate change. This is my last slide, I promise. This was a colleague of mine on the National Academy study, and he published this opinion piece in The Conversation, where he says, refusing to engage with solar geoengineering also raises questions. Can we be sure that we won't need it in the future? What if greenhouse gas warming generates horrendous climate impacts? And if it turns out that this is not technically feasible or socially acceptable, which is very, very possible, should we not learn that now? So with that, I will stop, and thank you very much for spending an hour listening to me talk about this. Appreciate it.
Thank you, Jim. Thank you, Jim. That was really interesting. We have some time for some questions. Anyone? Perfect, Amy.
Didn't even have to throw it. A fantastic talk, Jim. Thanks so much. I guess going back to the Pinatubo example, which is that kind of the classic example that everybody points to, and I'm in the same boat as you, where I think 1991 doesn't feel like it was that long ago, but it's actually 3 decades. And so I'm wondering, it must be the case that people have used that as a kind of calibration example for some of the models that you're describing for SIA, SAI, whatever, the aerosol injection, to see 5 years later, 10 years later, 20 years later, comparison with observations, not just say global mean temperature, but the geographic distribution of things like precipitation or temperature, all these things. So has that must have been done, right?
No, that's a really good question. And Pinatubo has been used in quite a few studies as a so-called natural analog, right? There were studies written by people that I worked with at NCAR that influenced my early thinking on this topic, that basically said, if you look at things like changes in regional precipitation after Pinatubo, there were some pretty big precipitation impacts. And this could be a real downside of geoengineering. Do we want to try to, do this permanently and produce those kind of changes? So there's been studies thinking about the impacts and looking, downstream multi-year, but maybe more pointed to your question, those kinds of observations and ongoing observations of, more recent volcanic eruptions. NOAA, for instance, has a program called SABRE, where they're now in a mode where they can rapidly fly and sample atmospheric conditions after volcanic eruptions to better understand how well we're representing some of these key microphysical aerosol processes in the stratosphere, and are the models really capturing that well? And I will just say that, all of our work has been done with the Community Earth System model, which I think one of its strengths is the so-called Whole Atmosphere Community Climate Model, WACCM, which has a very good, by many, many, many measures, a very good representation of stratospheric chemistry and stratospheric aerosol processes. But I have a postdoc in my group that just started about a month ago. Her name is Margot Klein. She's been involved in volcanic model intercomparison projects, and she's been leading one for Hunga Tonga. And she's showing that, there are big model differences in how these things are represented. And so this is, I'm very, very cautious. I can show you results that look very promising from CSM, but I'll be the first to tell you what those results are also highlighting, or where some of our big uncertainties are, and we have to better narrow those down. So there's a lot of fundamental, one of the things the Academy report also really emphasized is there's somewhat of an overlap. A lot of the questions that we need to be able to answer in terms of better representation, marine cloud brightening, cloud aerosol interactions, these are things we need to better understand anyway, just in terms of how the climate system operates and what climate change might mean for the future. So whether or not, geoengineering is in our future, a lot of the questions to better answer what the results of doing geoengineering would be are also required to answer what the future holds in terms of climate change or just natural variability.
We have a remote question. So I'd like to read out a question from Robert Stern. The public will be very suspicious of injecting stuff into the atmosphere. There will be many conspiracy theories advanced. How can this be dealt with?
And that has proven to be the case. There have been proposals to do pretty innocuous, very small scale experiments where one of the things the Academy report in 2021 paid very close attention to is we gave guidance that, first of all, we said that field programs, field experiments should not be done if the information can be obtained through laboratory-based experiments or through climate modeling experiments. But if important information can only be gained through field trials, we put a whole bunch of parameters around that, things should be injected in amounts. We quantify all of this in the report. I can't remember all the numbers right now. But so there would be no discernible influence on any aspect of weather or climate. Still, when some experiments, like some cloud seeding experiments over the Pacific have been proposed, or stratospheric aerosol injection experiments over some regions, the social pushback to that has been enough to shut all of those down every time they've been approached. So I'm not a social science expert, but we had social scientists on this Academy panel. And one of the things they really emphasized was how critical public engagement is going to be.
Yeah, I'd like to say Robert adds that without a massive public information campaign in advance, any experiment.
That's exactly right. So there has to be a very intentional public engagement on what this research is doing, what any of the risks from a real world field experiment might be, why we need to do this to advance the science. The public has to be part of this, not just, oh, by the way, we're scientists, we know what we're doing, trust us, we're going to do this thing, don't worry about it. That's never going to work on this. So this is actually a huge challenge in this field. And that's why I keep saying, it may turn out not to be socially acceptable, right? We may never get to a point where society, no matter what we say the potential benefits might be, it may never be acceptable to society. It's a scary thing. Alan Robach, who has studied this for a long time, likes to always say in his presentations, I wish we weren't talking about this. I wish this wasn't an issue. But I feel like I need to research it because people are thinking about it. And there's the risk that somebody's going to try to do something and perhaps they shouldn't be doing it. And I personally feel, and many others that are researching this topic feel, that the best way to address that is by doing the research to show what the risks could be of doing that. If we don't do this research, if we just kind of put our head in, this is my personal opinion, put our heads in the sand and say, scary idea. I don't want to intervene with the natural system. I want to fix things that we're doing, but I don't want to do it by kind of a Band-Aid approach. The risk of sort of ignoring that is that someone may try to do something. And
Yeah, I'd like to quickly add, and then we'll wrap up. Is there any status information, public information campaign?
Public information campaign?
Yes,
on
is there
what?
any kind of ongoing public information campaign in advance of experimentation?
Well, right now, I don't know of any field experimentation that is being planned, but I think that this would be a critical part of any kind of proposal to go out and attempt to study, even locally, how some of these techniques may actually work in practice. So there would have to be that. That's what the Academy report is emphasizing, that the public has to be a partner in any kind of a field campaign. But right now, I'm not aware of any that are planned.
Did you want to ask your question? Can you pass the mic to you?
I'm happy to stay after and take additional questions as well. And if you need to go, you're not going to upset me if you walk out.
Yeah.
It's fine.
Thank you very much for the very
Oh,
interesting
so that's a
presentation.
microphone. I thought he was going to throw it at me or something.
It's a microphone.
Okay.
Yeah, so you show that both mean and extreme precipitation decrease significantly over the land in injection simulation. It's a mostly thermodynamic effect of the cooler air
But
temperature.
certainly the changes in extreme precipitation are a very clear signal, right? And I think that's primarily thermodynamic. If the atmosphere is cooler and it holds less moisture, the Clapeyron relationship, then when it rains, you don't have as many heavy rainfall events. I didn't mean to give the impression that precipitation decreases everywhere over the land. What I was trying to emphasize is that there are projected changes in average mean precipitation or seasonal precipitation across the globe, but especially throughout the tropics under climate change. In general, stratospheric aerosol injection tends to reduce those precipitation changes everywhere. So where climate change is going to produce more rainfall or less rainfall, there's a little less rainfall or a little less drying under stratospheric aerosol injection. But there are regional patterns that emerge. And what I was pointing out in the context of Danielle's fire weather work is that where she found some of those, and please correct me if I'm saying this wrong, you're the lead author. Obviously, she's great, right? So she wrote a paper. I'm like, yeah, it looks good, submit it, and it got accepted. But there are regional changes. And so some of these changes, like over the Amazon, where drying is a big concern, that doesn't go away with stratospheric aerosol injection. And even in some of these experiments, it looks to be a little bit worse, even drier. And that's what we've analyzed here. But again, I would caution that, I think there's probably a large amount of variability between climate models and those kind of results.
Another related question, sorry. So in the previous study looking into the climate impact of volcanic eruption indicated that there is some transient response of the tropical Pacific climate system, like El Nino or La Nina-like pattern. And so when you inject the aerosol constantly, how does it affect the pattern of tropical climate?
So again, probably highly model and scenario dependent. So all I can tell you is that in the simulations that we have looked at, right, where very careful attention has been paid to not only trying to maintain global mean temperature, but not disrupt meridional temperature gradients. So the injection strategy is adjusted where the aerosols are injected and the amount of aerosols that are injected in these idealized model experiments are determined on a yearly basis, depending on how the climate system is responding. If that makes sense, there's like a control feedback algorithm. So in those idealized experiments, ENSO doesn't fundamentally change, nor do the teleconnections associated with the change in these experiments. But again, I would say that's very, very dependent on, exactly how we've designed these experiments. Okay.
Thank you so much for that interesting talk.
Oh, there you are. I was like, who's got the cue now? Okay,
sorry, sorry. Thank you so much for the interesting talk.
very welcome.
I just a quick comment, then I'll ask my question. I think a lot more resources should be devoted to understanding people's perception to what we scientists do generally. This is just beyond climate science, because there's been a really big increase in anti-science rhetorics. So I think telling people injecting anything into the sky, we might have riots. Then my question has to do with the machine learning approach you have to
yeah.
identifying patterns between the models with the SAI and the ones without.
Yeah.
Could you figure out why it couldn't identify the extreme precipitation?
Okay, it's not that it couldn't figure it out. What that result was showing is that stratospheric aerosol injection is effective at keeping extreme precipitation at the levels they're at in the current climate. So from a machine learning perspective, the computer was unable to identify whether it was sampling an SAI world or a world with climate change. It was just saying, I don't know, I can't tell. So it was right half the time and wrong half the time. It was flipping a coin. Okay, so that is an indication that stratospheric aerosol injection in these simulations was effective at preserving the current climate when it came to something like extreme temperature. Right.
Okay, thank you so much, Jim.
Yep. Thank you.
Thanks for staying over time as well. And also for students and postdocs that want to have lunch with Jim, we're actually going to be in the second floor conference room, and there's going to be a taco bar there. It's catered today. So, yeah. Yeah. So, yeah, thank you again.